Dear friends, in this video we want to tell you something about rolling of rigid bodies, and we'll do by means of examples. We will see different bodies having different shapes, and we make them rolling along a sloped board, and we see which one is taking more time or less time. And finally, we want to discover what is the time depending upon. In the first part of the video, we look only at the cylindrical bodies, which can be either full or hollow. On top, they can have different radius and width. Let's consider these four cases. A full can, an empty can, another full can but bigger, another empty can bigger. And the questions are, which is the quickest, which is the slowest, and what is the total dash-and time depending upon. For comparison purpose, we let them running always onto the same board, having a fixed slope and by pairs. The first pair is made by two equal size cans, 33 centiliters, one empty and one full. They are a cola and a cola light. As we can see, the full wins. The second pair is also made of two cans, but of different sizes. Both are full. One is cola 33 centiliter and the second is Red Bull 25 centiliter. Drawn. The third run sees two empty cans. They are of different foods, so size is different, both in diameter and width, and the weight is also different. Also in this case, drawn. What we observed is that the full can is quicker than the empty one, and the time of descent does not depend upon the geometry, neither diameter or width, nor upon the weight, and we need an explanation for that. The physics is telling us two laws, the first and the second dynamic equation. The first is saying that the mass times derivative of speed is equal to the sum of the external forces. And here we have the weight, also mass times gravity factor, and the friction. This is a static friction, very important. Without this force, we cannot have any rolling. We are now projecting those forces along the motion axis, that is the surface of the rolling board. Saying theta, the inclination angle of the board, the projection of the weight along this axis is mg times sine theta. The friction T is parallel to the board but opposite to the speed, therefore has a negative sign. The second equation says the moment of inertia times derivative of the angular velocity, omega point, is equal to the sum of the moment of the external forces. And if we take as reference for the moments the center of the roll, we observe the only external force taking place is the friction T. And if pure rolling, then the linear and angular velocities are linked together. We consider first the case of the full can. Therefore, the moment of inertia has this expression. Replacing it into the second equation and getting T, the friction force, from the first one, we can have an expression of the velocity derivative, which is a constant, 2/3 g times sinus of theta. And after two integration steps, we find also the space as a function of time square. To find the time, we need now to invert the equation and we get easily this expression, which is valid for the full can. Repeating the procedure for the empty can, where the moment of inertia is the double, we get this second expression, where only the factor within the square root has changed. First was 3 and now is 4. Let's make a check. We have a table of 2 meters, 71 centimeters high, and we produce now an inclination by raising the left side to 91 centimeters. We start now rolling the cans, this time in sequence, the empty and the full one. By the empty we get 2.77 seconds. By the full one we get 2.23 seconds. Definitely the full wins. Let's see what says the theory. By replacing the real values within the formula for the first scan, we get 2.85 seconds. The full one formula gives 2.47 seconds instead. There is a deviation versus experimental data of less than 3% for the first case and almost 10% for the second one. The 3% it's quite satisfactory, but 10% is much. In the real case, the full can is quicker than the theory. That means this is not purely rolling, but partially sliding. Now we want to understand if they are existing shapes quicker than the full cylinder. As we have seen in the formula, the descent time is the less is the moment of inertia divided mr square, like in the formula. And to answer this question, we need to consider the other possible geometries allowing rolling, therefore revolution shapes. There are many, of course. Aside from the cylinder, we have the full sphere, the hollow sphere, and then the cone, a double one for symmetrical reason. The last one has the minimum value, therefore it should be the quickest shape. Let's make now another race, full sphere against full cylinder. Actually, the experiment confirms theory. The full sphere is quicker. Now we make run two balls, both full but of different radius and different materials. We have the same time. If one of them is hollow, however, the full wins. I hope you have enjoyed this presentation and please let me know your comments. See you again.